Hello everybody, this is Homer White here with the 10th chapter of our course on tests of significance. This is part 1. In this part you'll learn about tests of significance for 3 of the basic 5 parameters. We'll look at tests for one population mean mu, tests for the difference of two means, mu1 minus mu2, and tests for a mean of differences in a population, mu_d. Always remember to make sure that the necessary packages are loaded. So let's talk about tests for one mean. First of all, let's get clear on the difference between confidence intervals, as you learned about them in the last chapter, and significance tests, as you're going to learn about them here. Confidence intervals are designed to answer this question. Given the data that you have, within what range of values might the parameter reasonably lie? A confidence interval gives that range of reasonable values. Tests of significance answer a little bit different question. Say that somebody thinks that a population parameter has a particular value. Given the data, is it reasonable to believe that the parameter is that particular given value, or is it not reasonable? Let's look at the fastest speed ever driven from our familiar Math 111 survey. So we're focusing on the variable fastest, and let's define mu to be the mean fastest speed ever driven for all Georgetown College students. Tests of significance in this chapter have the very same structure as tests of significance involving the chi-square statistic that we learned about long ago. In particular, there are hypotheses that you need to take into account. The null hypothesis is the claim that the population parameter is equal to some particular fixed number. So maybe somebody thinks that mu is 100. The alternative hypothesis is going to disagree with the null hypothesis in some way or another. In this case, we have what's called a one-sided hypothesis, the claim that mu is bigger than 100. So we call this a one-sided test. Here's a little bit of notation. Mu0 is what the null hypothesis thinks that mu is. So in our example, mu0 is 100. To produce tests of significance, we can use the same functions that we used to produce confidence intervals. Since t-test GC produced confidence intervals for one population mean, we're going to use that function again to produce tests along with those confidence intervals. All you have to do in addition is to set a new argument called mu to mu0, which is 100 this time. And there's another argument called alternative, and you'll set that to greater. That takes care of the alternative hypothesis that says that mu is greater than 100. And so the code for the test is very similar to that for a confidence interval. You don't need to give a confidence level if you want a 95% interval, but for the test you do need the mu argument and the alternative argument. Let's take a little tour of the output that you're going to see on your console. So if you haven't run that test for yourself, go ahead and do so, and then continue. The output begins with some descriptive results. And so we see the sample mean, x bar, 105.9 miles per hour. That's a little higher than the null hypothesis expected. Remember, the null thinks the population mean is 100. And so the expected value of x bar would be 100 if the null were right. So when we get 105.9, we're getting a little higher than the null hypothesis expected. Just as with confidence intervals, you have to wonder if you can trust the results of t-test GC. The standards for trust are exactly the same as they are for confidence intervals. Noticing that our sample is size 71, that's plenty bigger than our usual cutoff of sample size 30, we figure we're going to be able to trust the results of this test. Moving on to the inferential results in the output, we have a 95% confidence interval for the population mean mu. Since we are asking for a one-sided greater than test, we get a special kind of confidence interval. It's a one-sided interval. It has a lower bound of 101.77 miles per hour, but it has no upper bound. And so it says here the upper bound is infinity. So the way you interpret this interval is to say that you're 95% confident that mu is bigger than 101.77 miles per hour. Notice that that interval does not contain the null hypothesis' belief that mu is 100. So things are looking kind of bad for the null hypothesis at this point. Also in the inferential part of the output, you'll see some information about your estimator and its standard error. Our estimator, of course, is the sample mean x bar. It's 105.9 as we've seen. The standard error for x bar, computed using the formulas we've learned in other chapters, is 2.478 miles per hour. Now, the null expects that x bar is going to be about 100, give or take some for chance error. We got 105.9 for our x bar. Looking at the standard error, we see that that difference of 5.9 miles per hour is about 2 of these standard errors above what the null was expecting. So, if the null is right, these results are somewhat surprising. Things are still looking bad for the null hypothesis. Continuing on in our output tour, you get a report of the test statistic. The test statistic is called T, and it's defined as follows. It's the sample mean, x bar, minus what the null expects it to be. That's the mu naught value, 100 this time. And so what you see on the top is an observed difference between what you got in your study versus what the null was expecting x bar to be. In the denominator for T, you have the standard error for x bar. And so you are comparing the observed difference to the standard error through division. This test statistic looks a lot like the z-score that we introduced way back at the beginning of the course. It's a value minus a mean divided by something that works a lot like a standard deviation. So we say that the test statistic T has z-score style. What it's trying to do is to tell you how many standard errors x bar is above or below what the null hypothesis expected it to be. And as you can see, our results were indeed more than 2 standard errors above what the null was expecting. Again, things are not looking good for the null. Here is how the test statistic is actually computed. Simply plug in the value for x bar, the value that the null hypothesis thinks the mean is, the value for the standard error, and indeed you get 2.382. A little further on down, you get some information about the p-value for the test. Now, let's think about this a bit. T involves such things as x bar and the standard error for x bar. X bar depends on the data, so does the standard error. And the data comes to us by chance. So T is a number that depends on chance. Therefore, T is a random variable. As a random variable, it has some kind of probability distribution. And as you learned in the last chapter, it has approximately a t-curve distribution, where the number of degrees of freedom for the right t-curve is 1 less than the sample size. The sample size was 71 this time, 71 students in the survey, and so 70 is the number of degrees of freedom in our test statistic. So as a random variable, our test statistic will behave a lot like a t-curve with 70 degrees of freedom. This gives us a basis for finding a p-value. In this type of test, a one-sided greater than test, the p-value is the probability of getting a test statistic at least as big as the one we got if the null hypothesis is true. That vertical line should be read as if, or given that. So once again in words, we're looking at the probability that T is at least 2.382, given that the null hypothesis is correct. That probability is said to be about 0.009974. That's pretty small. So if the null is right, the results we have in this study are pretty unlikely. Here's a graph of the p-value. So we're simply looking at a t-curve with degrees of freedom 70. The total area underneath any density curve is 1. The area underneath the curve past 2.382, the value of our test statistic, is quite small. It's about 0.01. If you'd like to see a graph like this, along with your output, all you have to do is add an extra argument called graph and set it to true. How should we interpret that p-value in a practical way that people who don't take this kind of course could understand? Well, remember the p-value is about 0.009974, which we should round off a bit. That's about 0.01 or 1%. So we could say this by way of interpretation. If the null hypothesis is correct, if the mean population speed is only 100 miles an hour, then there's only about a 1% chance of getting a test statistic that's at least as big as the one we got in our study. When you put it this way, you can see we have a rather stark choice in front of us. Either the null hypothesis is correct, but then we have to maintain that we got a very unusual sample, one that would occur only about one time in 100, but occurred the one time we took the data. Or we could say that H0 is not correct, that mu is actually bigger than 100. Perhaps that's a better explanation for why we got a sample mean that was so far above 100. Since that 1% seems like a rather small chance, the second option does seem more reasonable in this case. Tests of significance for all of the basic 5 parameters follow the same format as tests of significance involving chi-square statistics. They're the same basic 5 steps to your argument. So when you're first writing out tests like this, it's a good idea to write out these steps in order. Remember that step 1 used to be statement of hypotheses. Step 1 here shall also be statement of hypotheses. But because a particular parameter is at issue, we'll include in this step a definition of the parameter using appropriate symbols, mu, and a good complete verbal description. So let mu equals mean fastest speed ever driven for all Georgetown College students. Once we've set up what mu means, then we can use it as a symbol and people will understand what we meant by it. So our hypotheses are null hypothesis, mu is equal to 100. In this course, the null hypothesis will always be a statement of direct equality, a belief that the parameter is equal to a particular number. The alternative hypothesis will always disagree with it in some way. In this case, it's the one-sided greater than hypothesis. Step 2 of a familiar test of significance is the safety check in reporting a test statistic. Well, by way of safety, we're thinking of our survey students, the 71 students we took from the population, as a random sample from the population. That's important. Also, the sample size n was 71, and that's large enough to trust the results of the test. Remember, 30 is our traditional cutoff. On to the test statistic. The test statistic is a very quick summary of the evidence that the data provides against the null hypothesis. This time the test statistic was 2.382. Our sample mean was 2.382 standard errors above what the null hypothesis expected it to be. This kind of interpretation is very good to add after you have reported your test statistic. You want to tell your audience what these numbers mean and how the argument is moving. Once you've reported the test statistic and interpreted it in this way, people can see already at this point that things are looking pretty bad for the null hypothesis. In step 3, we report the p-value. It was pretty small. We also give the interpretation of the p-value. If the null is correct, there's only a 1% chance of getting a test statistic at least as big as the one we got in our study. This interpretation is very important. It makes the case for how unreasonable it is for someone to continue to believe the null hypothesis in the face of the evidence that the data presents. The interpretation also makes your decision about the null hypothesis, that's step 4 of a test of significance, very clear. Since the p-value was very small, we're going to reject the null hypothesis. Our usual cutoff value for rejection is a p-value of less than 0.05. Finally, we try to make a non-technical and simple conclusion to sum things up. This data provided some strong evidence that the mean fastest speed driven at Georgetown College is more than 100 miles per hour. We can vary things a little bit. Let's try a new research question. Suppose that somehow we know that the mean grade point average of all University of Kentucky students is 3.3, but for some reason we don't know what it is in the Georgetown College population. Does the Math 111 survey data provide strong evidence that the mean GPA of all of Georgetown College students is lower than this 3.3 figure? The only population we don't know about is the Georgetown College population, so we've really only got one mean that we're interested in this problem. It's mu, the mean GPA for all Georgetown College students. A way of testing the hypotheses might be to say null hypothesis is that the mean equals 3.3. That's a way of saying that on average Georgetown College students are just like UK students. And the alternative hypothesis might be that mu is less than 3.3 if you think that the mean GPA of all Georgetown College students is lower than 3.3. Notice that this happens to be step 1 of a test of significance. We've defined our parameter of interest, and we've stated hypotheses for the test using our definition of that parameter. The code is quite similar. All we need to do is change the alternative to less rather than greater. Let's take a briefer tour of the results. This time the test statistic turned out to be minus 1.733 on 69 degrees of freedom. Remember, that's one less than the sample size, and if you're following along on your own computer and you've run this code, you'll notice the descriptive results showed that only 70 of the 71 students actually reported a GPA, and so it makes sense that the sample size minus 1 is a 69. Now the p-value is about 0.04. When you're doing a one-sided less than test, the p-value is a bit different. It's the chance of seeing a test statistic that is less than or equal to the test statistic that you actually got, if the null is true. Let's take a look at that graphically. So we're looking at a t-curve with degrees of freedom 69, and we think that as a random variable, our test statistic behaves a lot like this t-curve. We're wondering, what's the chances of getting negative 1.733 or less, 1.7 standard errors or more below what the null is expecting, if the null is really right? Those chances are represented by the shaded area that you see. And that shaded area is only 0.04, 4% of the total area underneath this t-curve. So the way you might interpret that is to say that if the null is correct, then there's only about a 4.38% chance of getting a test statistic that is less than or equal to the one that we got in our study. You can also do a two-sided test. So your first step might be, let mu be the mean GPA of all Georgetown College students, and you state the null hypothesis in the usual way, but look at how the alternative disagrees with the null this time. It doesn't have a side to it. It doesn't express the belief that the mean for Georgetown College students is bigger than 3.3, and it doesn't express the belief that it's less than 3.3. It just says that it differs from 3.3, one way or another. This is a two-sided test. And so the code for it requires setting the alternative to two-sided. When you run this test and look at your output, you'll see that a lot of things are the same. The descriptive results are the same. The estimator x bar is the same. The standard error for x bar is reported to be the same. The test statistic t is still the same, negative 1.733. That's because your sample mean was still 1.7 standard errors beneath what the null was expecting. Degrees of freedom is still 69, one less than the sample size. But look at the p-value. Used to be about 0.04, and now it's about 0.08. Why is this? Well, for a two-sided test, the p-value is defined to be the probability that t is less than or equal to the test statistic that you got, or bigger than or equal to the positive version of the test statistic that you got. That's going to be twice as big as before. Let's see why by looking at a graph. T-curves are symmetric. If the area before negative 1.733 is about 0.04, then the area after 1.733 will also be about 0.04. So the total area is about 0.08. You might wonder why we include both tails of the t-curve in our computation of a p-value. It's because at the beginning of the study, we didn't have a particular opinion about whether mu was bigger than 3.3 or less than 3.3. Because of that, it seems fair to examine just the size of the test statistic, to see how far the test statistic is away from zero, rather than looking for it to be a certain amount below zero or a certain amount above zero. So we have to think about how to do the interpretation in a two-sided test. We might say this: if the null is correct, then there's about an 8.6% chance of getting a test statistic at least as far from zero as the one that we got in our study. The at least as far from zero helps to capture the idea of being at least 1.73 units away from zero, either in the negative direction or in the positive direction. Notice that this p-value is bigger than 5%, and so we would not reject the null hypothesis in this case. You're probably wondering, when should we do a one-sided test, and when should we do a two-sided test? Let me offer this rule of thumb. If you have some prior evidence that mu differs from mu naught in a particular direction, really solid evidence based on data maybe, rather than just an impression you might have or a bias that you might have. If you've got that kind of prior evidence, then you can set up a one-sided test for that direction. If not, then just perform a two-sided test. When you've got that prior evidence, setting up a one-sided test, where p-values tend to be lower, is a rough way of incorporating the evidence that you already have and combining it with the new evidence that you get with the new data. But if you don't have that prior evidence, and you're just starting fresh, then a two-sided test is most appropriate because you don't have any prior impressions about whether the mu ought to be bigger than the mu naught or less than the mu naught. Let's now turn to tests about the difference of two population means. So thinking again about the Math 111 survey data, does that data provide strong evidence that Georgetown College males drive faster on average than Georgetown College females do? Again, we define our parameters and state hypotheses. Let's let mu1 be the mean fastest speed of all Georgetown College females, and mu2 be the mean fastest speed of all Georgetown College males. If you think that sex really has no impact on how fast somebody drives on average, then you would think that mu1 is equal to mu2. Another way of putting it is, you would think that mu1 minus mu2 is 0. So the null hypothesis is making a claim of no relationship, on average, between sex and fastest speed driven. Let's take a two-sided test here, and so the alternative hypothesis is just saying that mu1 minus mu2 is not 0. So the code is very similar to that for confidence intervals, except that we add the argument mu equals 0. Notice that the argument is still called mu, even though we are dealing with the difference between two population means. Again, the alternative is specified as two-sided, but it's a nice tip to know you don't really have to specify the alternative as two-sided if you're planning to do a two-sided test. That's the default value for the alternative argument, so you could leave it out. Notice also the familiar formula when we're studying the relationship between a numerical variable like fastest and a factor variable like sex. It's numerical twiddles factor. Taking a tour of the results, the descriptive results are shown first. So sample mean for the 40 females in the study was 100 miles an hour. Sample mean for the 31 males in the study was 113.5 miles per hour. Both sample sizes were at least 30. We're going to assume that these are two independent simple random samples from the two populations, the population of all females and the population of all males. So, in terms of safety checks, it looks like we can go ahead. Turning to the inferential results, our estimator for mu1 minus mu2 is the difference of the sample means, the x1 bar minus the x2 bar. Since the females were the first group, and they were at 100, and the males were the second group at 113, the difference is negative, negative 13.4. Now the standard error for x1 bar minus x2 bar is about 4.9. So notice that x1 bar minus x2 bar is nearly 3 standard errors below what the null hypothesis expected it to be. This looks kind of bad for the null. A 95% confidence interval for mu1 minus mu2, and that should be a minus right here, is negative 23 miles per hour to negative 3.5 miles per hour. Notice that this does not contain 0. That's the null hypothesis's belief about mu1 minus mu2. Since a confidence interval delivers a range of reasonable values for mu1 minus mu2, when 0 is not in that interval, it's as if the data is saying it's not reasonable to believe that mu1 minus mu2 is 0. So again, things are looking bad for the null. How about the test statistic? It's computed as negative 2.725. The formula for the test statistic is the observed difference, that is, the difference that we see between the two sample means, divided by the standard error for this difference. You can still think of this as being z-score style, because we've got a value from our data, x1 bar minus x2 bar, and we can imagine subtracting off 0, which is what the null expects it to be. When you subtract off 0, it doesn't make a difference, and so the 0 is not shown in the formula. But we can still see a difference between what we got and what the null expects, and we're dividing by something like a standard deviation. So again, this test statistic exhibits z-score style. And what's really important to keep in mind is that it still says how many standard errors our results are above or below what the null hypothesis expected it to be. And that should be a x1 bar minus x2 bar, not just an x bar. Since it worked out to negative 2.725 this time, then we can say that the observed difference between the sample means was 2.725 standard errors below what the null hypothesis was expecting. So our results are pretty surprising if the null is right. Again, this makes the null look pretty shaky. How about p-values? When you're dealing with the difference between two population means, the test statistics t is still a random variable, but it doesn't have any one of those t-curve distributions exactly. However, there's a method for picking amongst all the t-curves one that has a distribution most like the random variable t that you're really interested in. The formula for the right degrees of freedom is rather lengthy and we don't deal with it here, but R will compute it for you. Turns out that a t-curve with 55.49 degrees of freedom is one that's liable to be closest to the distribution of the test statistic. And so the way we get our p-value, since this is a two-sided test, is to compute the chance of the test statistic being less than or equal to what it was, or greater than or equal to a positive version of what it was. if the null is really right. That probability is pretty small, and indeed a graph shows that that's the case. In a t-curve with 55.49 degrees of freedom, there's not much area past 2.725 or before minus 2.725. So the p-value was a good bit less than our cutoff of 0.05, so we're going to reject the null hypothesis. Our conclusion is that this data provided strong evidence that Georgetown College males do drive faster than Georgetown College females on average. Now, some people don't like it when a difference of sample means comes out negative and confidence intervals based on it end up having negative numbers for their bounds. If you're one of those people, you might prefer to count Georgetown College males as your first population and Georgetown College females as your second population. So you might want to define mu1 to be the mean fastest speed of all Georgetown College males, and define mu2 to be the mean fastest speed of all Georgetown College females. So for you, Georgetown College males are the first population. For the function t-test GC, probably females would be represented as the first population because F comes before M. F for female comes before M for male in the alphabet. So how do you get t-test GC to recognize your choice of the first population? Well, all you have to do is take the argument first for the function and set it to male. So in the code, we have one additional argument, first equals male, in quotes. And then, if you run this code, and you should, take a look at the descriptive results, you'll see that males now come first, and the other elements of the output are all switched around accordingly. Let's take a moment to think about the basic argument that is being made when the p-value of a test is small. The first step in the argument is to suppose, just for the sake of argument and temporarily, that the null hypothesis is correct. If the p-value is small, then getting a test statistic as big as the one we actually got is a very unlikely thing. And that's why we conclude that it's not reasonable to believe the null hypothesis, because it's not reasonable to believe that something very unlikely to happen would happen the one time you try it out. Now, if the p-value is not very small, we're not going to be able to make that move from step 2 of this argument to step 3 of this argument, because we don't have the unlikeliness. You see, when the p-value is large, we might start off and say, suppose temporarily, and for the sake of argument, that the null is correct. Well then, getting a test statistic as big as the one we got is not so unlikely. The p-value is large. What can we conclude from this? Really, no definite conclusion can be drawn. We don't have strong evidence in this data against the null hypothesis. But we don't really have evidence for it either. That's the way tests of significance work when the null hypothesis states that the parameter is a specific single value. They never provide evidence for the null. They might provide evidence against it, but never for it. Common sense suggests, when you think about it, that the null hypothesis is almost always false, at least just a little bit. After all, what are the chances that the mean for some population turns out to be exactly 100 miles per hour, as in the fastest study, for example? So probably the null hypothesis in most practical situations is a little bit false at least. The name of the game in tests of significance is to see whether you could conclude that falsity just from the data alone. So, summing it up again, in this course, the null hypothesis is always going to be claiming that the parameter is a specific value, for example, that mu is 100. A low p-value provides evidence against the null, but does not absolutely prove that it is false. A high p-value does not provide evidence for the null, and it certainly does not prove that it's true. So when you get a high p-value, don't conclude things like the null is true, or say that you accept the null or believe the null. That simply isn't what's going on in tests of this nature. Finally, let's look at some tests for the mean of differences in a population. Let's take another look at the labels experiment. Remember, this was an experiment involving 30 subjects, and each subject was taken into a room where there were 2 jars of peanut butter on a table. One jar was labeled with Jif, the brand name, and the other was labeled with the Walmart brand, Great Value. And people generally know that Jif is the more expensive brand. Each person in the experiment was asked to take a taste from each of the jars of peanut butter and to give a rating of quality ranging from 1 to 10 for each peanut butter, where 10 is the highest quality. And remember that what the subjects didn't know is that both jars contained exactly the same peanut butter. It was the Great Value peanut butter. So hopefully any differences in their ratings were due to their perceptions about the labels rather than to differences between the peanut butter. So when you're setting up a test of significance for this situation, you could let μ_d be the mean difference in rating, Jif minus Great Value, and you always want to specify which way the difference goes, for some appropriate population, in this case, for all Georgetown College students. So the hypotheses would be, null hypothesis is that μ_d is 0. That represents the belief that the label makes no difference. On the other hand, if you think that labels make a difference, you might think that μ_d is non-zero. Here's how t-test GC works for a mean of differences. If the 2 numerical measurements are both present in a data frame, as it is in the case with the labels data frame, then your formula data input looks like this. A twiddles first to just signal the presence of a formula, and then the name of the variable that represents your first rating, then a minus sign, and then the name of the second of the 2 numerical variables. So that little subtraction that's indicated here sets up the paired differences that are the subject of your interest. You also, of course, need to specify the data frame, and you need to specify the null hypothesis. We don't need to say anything about the alternative because by default that's 2-sided, and we do plan a 2-sided test. Let's think about safety considerations before we go any further. We're hoping that the 30 subjects in this experiment were like a simple random sample from the Georgetown College population at large. The sample size is 30, which is right at our usual cutoff value. So why don't we go ahead and just check the sample for signs of strong skewness or for extreme outliers. What we need to do here is focus on those differences. Since those differences are not present in the original data frame, we'll need to make them for ourselves. We'll use the chapter book notation to do so. So labels $Jif rating isolates the variable Jif rating in the labels data frame. Then we're going to subtract off labels $Great Value rating. All that could be done on one line. And we'll store the results in an object we call diff. Let's take a quick look at a numerical summary of diff using favestats. When we look at favestats, we see that the minimum of the differences is -5. And so there's someone out there who gave the Jif labeled peanut butter 5 points lower rating than they gave to the Great Value rated peanut butter. The maximum of those differences was 8, so somebody rated the Jif 8 points higher than the Great Value. So if we want to make, say, a histogram of the differences, then we have our formula, twiddles diff. We don't need to specify a data frame because diff is just present in the global environment since you created the variable up here. We give a nice label for the x-axis, a reasonably descriptive title, And why don't we just make the histogram give us counts rather than percents or a density histogram? And here's a nice touch. We've looked at the min and the maximum value, and we know that all those ratings were whole numbers, so all their differences will be whole numbers. So it would be nice to have the rectangles of the histogram be centered over whole numbers. We can do this by having the breaks go from 1/2 less than the smallest value, so that's a minus 5.5, up to 1/2 bigger than the largest value in steps of 1. And we use the sequence function to accomplish this. So here's the histogram. It's a little bit perhaps left skewed, and maybe one or two of the values should count as an outlier. So we're noticing three things. We're noticing some left skewedness and a possible outlier or two. Also, we know that the data that we're collecting here has only integer values as its possibilities. It's not really continuous data at all. All of those things could be a problem at smaller sample sizes, but given that the sample size is up to 30 here, we're probably okay to continue. So looking further down into the output, we see that d bar, which is our estimate of mu d, turned out to be 2.367. The standard error for d bar is about 0.5. Again, think about what this all means. The null hypothesis expects d bar to be about 0, give or take some for chance error. We actually got a d bar of 2.367. And when you think about how many 0.5s are in something that's around 2, then you see that our results are more than 4 standard errors above what the null hypothesis expected. This does look bad for the null. The 95% confidence interval for mu d is reported to be 1.31 to 3.41 rating points. Notice that 0, which is the null's belief as to what mu d is outside of this interval. So again, things are looking bad for the null. Now the test statistic for a mu d situation is again defined in z-score style. It's the d bar you actually got minus what the null expects the d bar to be divided by the standard error for d bar. So once again, it's an observed difference between your results and what the null was expecting as compared to the standard error for those results. Z-score style again. Again, what's really important to remember is that your test statistic says how many standard errors d bar is above or below what the null hypothesis expected it to be. It was indeed more than 4 standard errors above what the null was expecting. Turning to the p-value, the behavior of t as a random variable is very similar to what you would see with just one population mean. If the null hypothesis is true, then the t statistic should be approximately like a t random variable with 29 degrees of freedom, one less than the sample size. We're doing a two-sided test, and so the p-value is the chance of getting less than or equal to negative 4.6 or at least 4.6, the test statistic that we got. 2 tails for a two-sided test. Again, this is all conditional on H0 being true. So if the null is right, the chances of getting results like what we got are about 7.42 times 10 to the negative 5. The E in the output represents a 10 raised to the power of negative 5. To interpret the p-value in a simple way, let's first look at a quick math review. When you raise a number to a negative power, it's the same as the reciprocal of that number raised to the positive power. So 10 to the minus 5 is the same as 1 divided by 10 to the 5. Now 10 to the 5 is 5 tens multiplied together. That turns out to be a 1 followed by 5 zeros, so that's 100,000. Therefore, 10 to the minus 5 is 1 divided by 100,000. So you could say a 1 in 100,000. 7.42 times that figure, or if you think of it just 7 times that figure is 7 in 100,000. So we can say this by way of interpretation of the p-value. If the null is true, if the labels make no difference, then there's only about a 7 in 100,000 chance of getting a test statistic that's at least as far from 0 as the one we actually got. Think about it. If we did this experiment 100,000 different times, only in about 7 of those times would we get a test statistic that's as extreme as the test statistic we got. But we got it the one time we actually did the experiment. This looks really bad for the null hypothesis. So the p-value is less than 0.05. We're definitely going to reject the null. This data provided some strong evidence that for the Georgetown College student population, jar labels affect the perception of the quality of peanut butter. By the way, if you're running lots of tests and you don't need to see quite so much output to the console, you can limit it. You can set an argument called verbose to false. So if you add this one extra argument to any t-test call, then you'll get a confidence interval and you'll get a test statistic and p-value, but not much else. Thank you for listening.